Popular Class D audio amplifier boards overview. Audio amplifier evolved to Class D technologies. They started in professional audio where power, weight and reliability are more important than tiny bits and pieces of distortion. But the magic happened, and with specialized gate drivers and high power fast switching MOSFETs development, Class D audio amplifier quality dramatically improved. Today we are close to the moment when the audiophile audience accepts the supremacy of Class D architecture. In this video, we will walk through leading Class D OEM boards manufacturers Hypex, ICEpower and Purifi products and take a closer look at the most popular Class D boards. This is a long story and I split it into 4 parts. To understand one or another statement, we will start with Class D amplifier building blocks overview. There is no secrets or magic in Class D amplifier design. Most building blocks are well described in components manufacturers' white papers and reference designs. The majority of eBay boards sold by China manufacturers are implementations of reference designs. The same is relevant to famous manufacturers like Hypex and ICEpower. By analyzing one or another mentioned company's design, you will find familiar building blocks in their finished products. For common language, we need to agree about a basic criteria when we are describing amplifier and comparing them. First, about power. To have a good audio system, we should work away from clipping and be able to drive speakers to Xmax without excessive amplifier distortions. So, for your system you need amplifier with 2 to 3 times power to the speaker RMS. Second, we should agree on how we rate a high-quality amplifier power limit. Let's agree that the maximum usable power is rated at 0.1% total harmonic distortion, what is the human hearing limit, and best in a world-class speakers total harmonic distortions. The majority of us, including me, don't have the best in the world speaker systems and should live with a standard speaker total harmonic distortion performance of 1%. There is significant gap between speaker performance and amplifier performance today. And audio amplifiers continuously improving, but speaker systems practically not. Amplitude frequency characteristics within 0.25 decibels in full bandwidth. It's not so critical parameter. We will not be able to hear the difference between 15 Hz rated system and full bandwidth. Let's remember that in electronic recording we have hard bandwidth cut at 20 kHz. And there are no harmonics above 20 kHz in audio recording. The statement that your speaker tweeter can go up to 40 kHz doesn't make your system sound better. That means that you just have a smaller size tweeter. It is more marketing statement. Damping factor, about 50. It is related to the audio amplifier output impedance, and it is important in dealing with passive crossover high energy storage inductivities and capacitors. 50 and above on 4 ohms is good, above 100 it's excellent, and there is not much improvement going above 100. With the latest generation MOSFETs you can achieve fantastic figures of damping factors of 500 and above, often used for marketing purposes. Basic principles of Class D operation. At amplifier input, music signal is creating pulse-width modulated signal. After that we insert deadtime and level shift for high power MOSFETs and amplify pulse signal practically to power supply rail voltage. Then we filter carrier frequency with LC filter and get back amplified audio signal. The audio signal is proportional modulation depth multiplied by the amplification factor of the power stage. Due to the switching output stage we achieve high efficiency. There is more detailed picture of the output signal. In practice, this process is rather complicated and you need to provide a number of high tolerance electronic blocks. There are errors due to the finite MOSFET switching performance. There are errors due to the output filter nonlinearities. And there are bus pumping effect where switching MOSFETs working as a voltage multipliers. For details, read manufacturers' white papers where physical process and remedies are well described. For the switching stage reliable performance you need to insert so-called dead time. That means there is always time when both switching stage transistors are in the closed state. It is creating similar distortions like to class AB output stage. Pay attention to the graphs, how total harmonic distortion relates to the dead time. In practice, for high power amplifiers like 300 watts and above, dead time is about 100 nanoseconds. But it's not so dramatic because we compensate sets in total harmonic distortions with negative feedback and get a system performance around 0.005%. Inductor selection is critical and determines system total harmonic distortions a lot. You can see from graphs, output inductor can degrade your system total harmonic distortion 100 times. One more reason to purchase Class D systems from proven manufacturers. Most of the high tolerance electronics are integrated into the so-called gate driver chipsets. There are not so many companies in the world manufacturing those units. Infineon is leading gate driver production. There are a couple of gate drivers that you will see practically in all famous Class D board designs. I think that even ICEpower is using standard Infineon gate drivers in its design, with ICEpower prints on some of the chipsets. It is true hypothesis from my side, with no evidence, just thinking loud. In practice, you should have a really powerful design capacity to develop chipsets and purchase minimum quantities from the chip manufacturer. But maybe I'm wrong. IRS 2092 is by far the most popular gate driver that you can find in a large number of designs. With the driver, you can build up to 500 watt capable Class D amplifier. This driver is simplifying your design effort a lot and contains many critical functions like protection, pop-up noise limiter, programmable dead time management, etc. There is basic connection diagram. This chipset requires 12 volts stabilized additional service voltage. There you can see real working design schematics, well known as Iraudan 7S. I would say the design is relatively simple, and with good selection of electronic components you can make an amazing performance amplifier. Two-channel version with some extra functionalities like thermal protection circuits and synchronization pin for bridged connection. I guess that this particular gate driver has been used in famous ICEpower 125A6 too. There is basic connection diagram. Very simple to build a stereo amplifier. And this is practical schematics from International Rectifier Library. Schematics, bill of materials of components and board layouts are provided in reference design support documentation. There is closer look to the chipset. And this is a gate driver for high power solutions with rail voltage up to plus minus 200 volts. You can build high quality kilowatt capable designs. My guess is that some ICEpower kilowatt capable designs are based on this chipset. But don't forget about the power supply. For kilowatt designs, a lot of costs are associated with the power supply and effective protection circuits. Here is 4-channel gate driver, the same characteristics as for the stereo version. I haven't seen designs of this gate driver yet, but it may be a good design for 3-way speaker systems where 2 channels are connected in the bridge for a woofer and 2 channels in a single-ended connection for mid-range and tweeter. Why there are no such design in market? I think it's price consideration for a board. You can build a better design using 2 ICEpower 125A62 boards, separating woofer driver power supply from mid-range and tweeter board. There is one more chipset, what you can find in many designs. It is Texas Instruments TPA3255. Integrated chipset gate driver and power MOSFETs with a great performance characteristics. You can build a perfect amplifier up to 150 watts per channel on 4 ohms, as well as multi-channel solution. This is the best price-performance solution that you can find today. Output power up to 200 watts on 4 ohms. Total harmonic distortions, great. All outputs in parallel to drive 2 ohm load up to 600 watts. Maybe used for applications where 2 4 ohm woofers are set in parallel connection. Still acceptable performance. Typical stereo BTL application. This is the most popular design that I have seen. 4 channels configuration. You may combine 2 outputs in BTL for the woofer and 2 outputs for a mid-range and tweeter via capacitor. For mid-range and tweeter, output capacitor resistance is negligible. It may be an interesting solution for budget active 3-way high-performance speaker system. Parallel BTL, subwoofer monster of massive power. And summarizing, TP3255 has amazing flexibility, especially in connection with DSP crossover. There are some potential for a great three-way speaker projects when the budget is critical. Another important component for a great audio amplifier is a power supply. In reality, power supply costs are higher than the amplifier stage. Class D power amplifiers are sensitive to power supply voltage fluctuation, therefore classical mains transformer power supplies don't suit for Class D amplifiers. You need a regulated low noise switching mode power supply capable of working with almost no load to max load conditions. There is fundamental difference between industrial power supply requirements and audio amplifier requirements. Music signal power density is just 1/8 of cinewave signal. We still need 1 kW power capability for 1 kW amp, but we can save on massive heatsinks due to the average power consumption of just about 200 watts. There are certifications regulations on how our equipment uses mains electricity. Switching mode power supply is capacitive load that introduce specific distortions to mains electricity. We need to understand some power electricity terms, and the first one is power factor. For pure resistive load like consumer heater, consumed voltage and current are in phase, and you get a maximum power out of the mains. For capacitive load like switching mode power supplies, we have phase shift, and we cannot effectively use mains provided power. When building consumer equipment, you have regulations where above the termed mains power consumption you should have specific power factor correction circuits. In addition, such designed power supplies have better output voltage regulation and overall efficiency. There are more problems with capacitive load power supplies. In figure 1.3 you can see that charging current has pulse form. Pulse form introducing a number of harmonics that making your power supply system noisy. Another reason to use a power factor correction circuits in your design. On the right side you can see one of the power factor correction circuits. It is working schematics provided as a reference design. The basic principle is based on the inductor and voltage multiplier, rising incoming rectified mains to fixed voltage value, typically 390 volts. Such schematics is working in a large input voltage range like from 85 volts to 250 volts. These are the main building blocks. Input filter to filter switching noise back to mains, voltage multiplier, and PFC driver chipset. What else do we have? There is flyback low power switching mode power supply for standby and services voltage, and some schematics for automation purposes. LLC resonant switching mode power supply design. I did not find an exact definition of abbreviation LLC. I guess that the meaning is 2 inductors and 1 capacitor. LLC resonant architecture is absolute winner when we are talking about audio power amplifier power supply. It is capable to work from almost no load to maximum performance. It has the highest efficiency among different switching mode power supply designs and the lowest electromagnetic interference noise. As a lowlight, they cannot work with a broad input voltage range. You need either manual or automatic switching between 110 volts mains and 220 volts mains. And designers need excessive magnetics knowledge to properly design such power supplies. Basic operation principles. LLC resonant switching power supply consists of 3 parts: square wave generator or gate driver, resonance circuits, and rectifier with a filter for DC output. The basic principles of LLC switching mode power supplies is creating a resonance system where leakage inductivity and a series capacitor is making resonance system for calculated driver operation frequency. Working frequency is a bit higher than the resonant frequency. Closer to resonance brings higher output voltage and vice versa. Such architecture is bringing 2 benefits. First, due to the resonant contour we have a cinewave type of current flowing through the transformer and therefore similar output voltage. You don't need the large inductivities to filter out DC voltage. Second, your gate driver all the time generating symmetrical pulse form with a 0 switching noise. As you can see, all regulation is done just by changing frequency. This is significant benefit comparing flyback architecture with the pulse width regulation principle. There are real application schematics. From the left side, you can find a gate driver and components and low power transistors to drive the power switching stage. The main transformer with the leakage inductivity, transformer inductivity, and resonance capacitor. All the complexity of design is hidden in this part. Secondary winding and low losses special rectification diodes. Physical appearance looks similar to power MOSFETs, and for high power solutions, rectifier diodes are placed on heatsink. The tricky thing is a mains transformer. The transformer needs to be winded in special way to create large parasitic inductance, called leakage inductivity. And of course output filter for secondary voltage. And finally, feedback circuits for gate driver to stabilize the output voltage. And sometimes you need service voltage for amplifier stage, and there is an example of high efficiency voltage down converter. 10 years ago I participated in designing LLC switching mode power supply with hands-on. Calculations are rather complex, and LLC driver chipset manufacturers support designers with online calculators. The practical design consists of the first calculation, after which you get reference values of resonant tank. Then you physically wind the transformer based on calculated values and find out what are realistic leakage and transformer inductivities. After that, we do several calculations until getting figures of what we can achieve in a practice. Typically, gapped ferrite cores are necessary to get the right values. And you should do the process from scratch each time an output voltage and power specifications changing. That means for each modification of the output power and voltage you need to do a new resonant tank design. But it is amazingly good power supply for audio amplifiers. And summarizing part 1. The power supply is a very important element of the good Class D amplifier, and it is far more complex design element than the Class D amplifier itself. Actually, only integrated solutions are worth reviewing. In my overview, I will focus mainly on the integrated boards for high-end audio performance. In the next part, we will look into Hypex Class D amplifier products and pick some models for closer analysis. You may be surprised how many familiar components you may recognize in this company designs.